In example number 1, we're looking at describing the motion of an object that is in a two-dimensional plane. So in this case, we're looking at a radio-controlled model car that is placed in a vacant tennis court. And so you can imagine that on this tennis court, we've placed a grid. And we've chosen some place on that tennis court to be the origin, and then we've laid down an x-axis and a y-axis here. And then you start time at some point while it's moving in a straight line, and at 2 seconds you measure it having coordinates of 4 meters and 2 meters. That means it is 4 meters from the origin horizontally and 2 meters up, and this is labeled as position 1. And then at a later point in time, t2, at 2.5 seconds, the car now has a position P2 here labeled at 7 meters away from the origin horizontally and 6 meters up. These numbers here that are labeled are called the coordinates at each of the point 1 and point 2. The vector that goes from the origin to point P is called the position vector. And this position vector, r sub 1, has components along the x-axis and along the y-axis. And you can find the magnitude of r1 by using Pythagorean theorem, if you know the x-coordinate and the y-coordinate. And the same thing can be done for position 2 with respect to the origin. And I'll label that as r sub 2 for that position vector 2. And we could find the displacement between these two positions, which I'll label as delta r. And delta r would be equal to r sub 2 minus r sub 1. Once we know that displacement between position 1 and position 2, we can then find the average velocity by taking the displacement vector r and dividing it by the time interval delta t. Well, it turns out it follows that this change in position can be broken up into a delta x along the x-axis and a delta y along the y-axis. So this would be the horizontal displacement and the vertical displacement. And so therefore you could describe the average velocity in terms of two components. You could use the horizontal displacement divided by the time, and that would give you the average velocity along the x-axis, or you could find the average velocity along the y-axis by taking the vertical displacement and dividing it by the time interval. In this question, that's what we're looking for. We're looking for the components of the average velocity of this car. So as this car moves from point 1 to point 2, we want to know what was the average velocity as it was moving along the x-axis and what was its average velocity along the y-axis. So we're breaking up this average velocity into two components, the horizontal component and the vertical component. So the displacement along the x-axis, well, you can see that it started off at 4 meters horizontally, and then at point 1, and then point 2, it ends up at a displacement horizontally of 7 meters. So to find the horizontal displacement, it's 3 meters. We got that by doing 7 meters minus 4 meters. That gave you a displacement of 3 meters. And then the time interval, in this case, is from 2.5 seconds minus 2 seconds. So 2.5 seconds minus 2 seconds, that gives you 0.5 seconds, and that's an answer of 6 meters per second horizontally. That's how fast the car is moving along the x-axis. Then we look along the y-axis that is defined here in our plane. And looking along the y-axis, it starts off at 2 meters and then ends up at 6 meters. So we do the final position, 6 meters, minus the initial position vertically, 2 meters, and then the same time interval here on the bottom. And that will give you 4 meters divided by 0.5 seconds, which gives you 8 meters per second horizontally, or along the along the y-axis. Now that we know how fast it moves in the x direction and how fast it moves along the y direction, we then can find the resultant velocity along the position vector delta r. Think of it, you have along the y-axis 8 meters per second, that's the average velocity of the y-axis, and then along the x-axis you have an average velocity of 6 meters per second. So we're looking for this velocity right here, the average velocity of both of these combined together. And so hopefully you're thinking, well, that's a nice right triangle. If you were to put this over here now, you would then find the average velocity by taking the average velocity along the x-axis squared plus the average velocity along the y-axis squared. Then substitute your numbers in. We have 6 meters per second quantity squared plus 8 meters per second quantity squared, which gives you an average velocity of 10 meters per second. And that's the magnitude, by the way. We still need to find the direction of that. So we're looking for this angle theta. So the angle theta can be determined by, well, that's right in here. Remember that this along the y-axis here is the average velocity along the y direction here. So we could use the arctan of the opposite, which is the average velocity along the y-axis, divided by the adjacent, which is the average velocity along the x-axis. Let's substitute in. We have 8 meters per second divided by 6 meters per second. And when you do the arctangent of that, you will get an angle of 53 degrees above the x-axis. So the average velocity of our remote control car is 10 meters per second at an angle of 53 degrees above the positive x-axis as defined in our picture up above. By the way, this was part A over here. This is part B. Now, you could get part B in an alternative solution. How could you do it? Think about it. You could just use this, right? You can find the displacement. I'll just write alternate solution. The alternate solution here would be the average velocity is the displacement divided by the time. And the displacement is really the displacement from position 1 to position 2. So it went a displacement of 3 meters, and here 4 meters. This is 3, and this is 4. What was its actual displacement here? Yes, that's 5 meters. So this is 5 meters divided by 0.5 seconds by using the Pythagorean theorem, and this gives you 10 meters per second. Furthermore, you could get the angle by doing the arctan of not the velocities, but the displacement along the y-axis and the x-axis. So that would be arctan of, what was it along the y-axis? That was 4 over 3 here, which gave you 53 degrees, the same answer that we had before. Now this is true. You can use this as long as the object is moving at a constant average velocity. If you had accelerated motion, then you have to bring in your kinematics equations. And remember that the average velocity may not always be in the same direction as the displacement. So I wouldn't trust this alternate solution always, because this is only true just because the car is moving at a constant average velocity. But if you can imagine, if you could take the tennis court and sort of tilt the axis so it accelerated and the path wasn't a straight line but it started to curve like this, then the average velocity wouldn't be in the same direction as the displacement vector. So just be careful with that. Second alternate solution, that doesn't always work. It only works if the displacement vector is in the same direction as the average velocity vector. All right, that's it for example number 1.